Hey, everybody. I'm Einar Urdshals, and I will present to you the work I recently did on crystal responses to general dark matter-electron interactions, together with my PhD supervisors, Ricardo Catena and Timon Emken, here at Chalmers University in Gothenburg, Sweden. And we also collaborated with Nicolas Baldin and Marek Matas at the ETH Zurich in Switzerland. Now, we modeled dark matter-electron interactions in silicon and germanium crystals, as these crystals are currently being used as detector material in direct detection experiments. Now, the way these experiments work is that one has a crystal in the ground state, and then a dark matter particle scatters off an electron in this crystal, exciting it from the valence band to the conduction band, and thereby creating an electron hole pair. And this electron hole pair can then be detected. Now, what's really interesting about looking at scattering of electrons is that these scatterings can be used to probe dark matter masses down below an MeV, and this is much lower than what one can go with nuclear recoils, simply because the electron is much lighter than a nucleus. Now, so far, this scattering of electrons has been modeled for simple models such as the dark photon model. But we are extending this to a framework in which we can treat any dark matter model that can scatter off these crystals in a direct detection experiment. And we are doing this using an expansion in effective non-relativistic operators. So these effective non-relativistic operators you can see here. So one can show that any Lorentz invariant scattering, which in the non-relativistic limit means Galilean invariant scattering, can be expressed in terms of these effective non-relativistic operators. So these are, for instance, just the identity for the first operator. Now this is the identity in the dark matter electron spin space, but it can also be, say, the dark matter spin dotted with the electron spin, or other terms at the lowest or at low order in transfer momentum divided by the electron mass. Now, what we show is that this rate of creation of electron hole pairs in these crystals can be expressed like this. So one has the usual integral over the deposited energy delta E, and over the transfer momentum Q, and also over the velocity of the dark matter particle here. And then one has what is essentially the matrix element squared. And we show that you can write this matrix element squared as a sum of 5 terms, each of which can be factorized into a dark matter response function R and a crystal response function W. Now, as the name suggests, these dark matter response functions R are functions of dark matter physics, such as the coupling to the standard model and the velocity of the dark matter particle, whereas the crystal response functions are functions of crystal physics, such as the electron wave function. Now, for the previously treated dark photon model, there the dark matter response function was simply either 1 or inversely proportional to q to the power of 4, depending on whether it's a heavy or light mediator. And there was then only one contributing dark matter response function, namely R1, and thus also only one contributing crystal response function, namely W bar 1. So this W bar 1 was the only crystal response function that was previously known. Now these crystal response functions are defined like this. Now they are, I mean, they are essentially just defined as some prefactor, and then one sums over the lattice vector G and the initial valence bands and the final conduction bands, and one integrates over the Brillouin momentum here. And what differs between the different crystal response functions is this BL. Now, BL is just different combinations of these functions that we call F prime and F vectorial prime, dotted with a Q vector. Now, these F prime and F vectorial prime, they are essentially just electron wave function of overlap integrals. So with the vectorial case here, one has, as you can see, a derivative in the initial state wave function. And for then different operators, one then get different ones of these crystal response functions that contribute. For some of the effective operators, one only gets one of the response functions, whereas for other ones, one gets multiple crystal responses. Now, we then use density functional theory to calculate these crystal response functions, and I will show you some of them here. So to the left here, you see the crystal response function for silicon, and to the right it's for germanium. Now on the x-axis here is the deposited energy delta E, whereas on the y-axis it's the transferred momentum Q, and the colored bar here gives the magnitude of the response function. Now there is this dashed line here, and the points below this dashed line are kinematically inaccessible for gravitationally bound dark matter. So it's really only these points above this dashed line that contributes to the rate of electron hole pairs that are created in the crystal. Now, as you can probably see here, there is some discontinuity at around 30 electron volts for germanium crystals. Now, this is caused by there being some deeper electron states in germanium, namely the 3D electrons. And at 30 electron volts, they become accessible, and they then also start contributing to this crystal response function. Now here you can see essentially the same plots, but for the second crystal response function. That's the one that is generated by this dot product between Q vector and the vectorial crystal response function times the scalar crystal response function. Oh, sorry, not the vectorial overlap integral times the scalar overlap integral. Now, here you can see the third crystal response function generated in terms of the vectorial overlap integral squared. And here you can see the fourth crystal response function. Now, once these response functions have been calculated, they can then be used to predict the rate of excitations in a silicon or germanium crystal. Now, just to illustrate what we can do with our framework, we take the anapole interaction, and this interaction is given by the Lagrangian you can see here. So it's essentially an axial vector coupling to the photon field. And one can then show that when one takes the non-relativistic limit, one obtains two operators, namely the O8 and the O9, and they have these couplings. And we can then obtain the rate at which electron hole pairs should be created. Now, at the plot to the left here, we have plotted this for a 10 MeV dark matter particle. And on the x-axis here, you can see the number of electron hole pairs created in a single event, whereas at the y-axis here, you can see the rate at which these events happen. So as you can see here, the most common is that a 10 MeV dark matter particle will create two electron hole pairs when it scatters. Now, the black dash dotted line here gives the total rate of created electron hole pairs. So this black dash dotted line here is what you will actually measure. Whereas the light blue line that you can see here gives the contribution of the first crystal and dark matter response function. The second one, the light green one, gives the contribution from the second one, and the orange one gives the contribution from the third crystal and dark matter response function. Now, these are not measurable, but we still show them to illustrate that all the different responses are important and give non-negligible contributions to the total rate. Now, on the right here, you can then see the corresponding exclusion limits. These lines here come from Xenon 10, Xenon 1 ton, and Darkside 50. So they are from a previous work by my collaborators, whereas this dark green line here comes from this work, and is from Sensei, which uses silicon, and the orange line is from the Edelweiss experiment that uses germanium. And what one can then see is that silicon dominates below roughly 5 MeVs, whereas below roughly 1 MeV, germanium dominates because germanium has a smaller band gap. So then, in summary, what we do is that we model dark matter-electron interactions in silicon and germanium crystals, and we do this because they can be used to model to probe smaller dark matter masses. And in this work, we derive a framework for the first time, which can be used to derive the rate at which electron hole pairs are created in these directed detection experiments for any dark matter model. Thank you very much.